Hello everyone. Today we cover the last section in this chapter that we're covering, chapter 10, 10.2, polar equations and their graphs. So in the last section we saw how to convert from polar to rectangular coordinates and how to plot points on the polar coordinates. Today we're going to use those to graph polar graphs. Two objectives we have today: identify and graph polar equations by converting to rectangular equations. So first, we already know how to graph things on rectangular coordinates, and we also learned how to convert from polar to rectangular. So the first method that we can graph polar equations is by first converting them to the rectangular coordinates and then use our knowledge of our previous knowledge of how to graph on rectangular coordinates to graph them. And then the next objective, we're going to plot points. We'll get to this one in the next video. So first, let's review some of the ways that we know how to graph equations in rectangular coordinates. We know if I have an equation in the format y equals mx plus b, this is a line with a slope m, and b is the y-intercept. We also know that if I have an equation in the format y equals a, where a is any number, that is a horizontal line. The equation x equals a, where a is any number, that's a vertical line. We also know how to graph circles. The general equation of a circle is this: x minus h squared plus y minus k squared equals r squared. We know that in this format, the center of the circle is h comma k, and we know that the radius of the circle is r. For example, x plus 3 squared plus y minus 7 squared equals 25. This is an equation of a circle. The radius is negative 3, because this is x minus h. The radius is negative 3 comma 7, and this here is, the center of the circle is negative 3 comma 7, and this here is the radius squared, which means the radius of that circle is 5. So if I know the equation of a circle that looks like this, I know exactly how to graph it. I have the center here, so I'm going to put a point on the center, and then 5 units each way from the center, I will graph my circle. Okay, so we'll see how that helps us graph polar equations by first converting them. Now, there is something that was important for us to remember when we were trying to graph equations of circles in previous math courses. There's a trick that we learned called completing the square. And basically completing the square happens in cases like this. So if I have x squared minus 6x, for example, equals, I don't know, let's say 0. And I want to complete the square here. I want this to be a perfect square trinomial. So I can put it in this format. I can put it as x minus something squared. The method of completing the squares says that I can take this middle number here, b. I can divide it by 2, so I can take 6. I divide that by 2, which gives me 3, and then square it. So 6 divided by 2 is 3, 3 squared is 9, and that tells me that the missing number that I need here for completing the square is 9. So what we used to do is we would add 9 here to complete the square, but that means that we also have to add 9 to the other side. And once I have this here on the left-hand side, the perfect square trinomial, I can factor it. This gets factored as x minus 3 squared equals 9 on the other side. So this method here of completing the square, we're definitely going to use it now again. Once again, we did this when we were graphing circles in previous math courses, specifically college algebra. If you do need any reminder of how we used to do this, or if you have any questions for me, feel free to ask or review how to complete the square or how to graph circles by completing the square in your notes from previous classes, but we will certainly use that skill here as well. Okay, so we know that we have a grid for rectangular coordinates. That grid is the XY grid, and we used to plot our points there and then, let's say, graph a line, or use that grid to graph any equation we want. Polar coordinates also do have a grid. The grid looks like this. It's a circular grid. Now we know certain things about this grid already. We know that this here is the pole, that point that coincides with 0, 0, and we know that this here is the polar axis. We know that every point that is in the polar coordinates consists of r and theta, where theta is the angle. So here theta equals 0, and then we have, for example, theta equals pi over 6, theta equals pi over 4, theta equals pi over 3, theta equals pi over 2, and so on. So theta is the angle, and the grid here certainly gives us all of the angles. Theta equals pi. So any point that we graph on the grid has its own theta. And then we have r, where r is the distance from the hole. So this point here is at a distance of 2. So here's 1, 2, 3, 4, 5, and so on. So on the grid, any point or any at any angle on the grid, we have 1, 2, 3, 4, 5. This is why that grid is a circular grid, as you can see. So let's say we take this angle, 7 pi over 4. Once again, here's distance 1, or r equals 1, r equals 2, r equals 3, r equals 4, r equals 5, and so on. So the polar coordinate grid is a circular one. We're going to learn how to graph equations on that grid. And because this is a circular grid, it is very useful for us to graph things that are circular on it. It's much easier and much better than using the rectangular coordinate system. So circles are much easier graphed and used with polar coordinates. Any circular patterns, we're going to see some of those. Radars, for example, you know that the radar is a circular grid like this. If you ever went on a fishing boat or something like this, you know that the radars are circular, the way that they detect the amount of fish, or what do you call it, like how much fish in each area, or detecting like the bottom of the ocean, and so on. That's a circular grid. It uses polar applications and polar coordinates in building those. Optical devices, directional microphones, you know, those mics that have directional capabilities, they're also circular. Even building Mount Rushmore, when they used machines to cut off the the rocks to build all of these shapes, the faces on Mount Rushmore, they used polar coordinates and polar grids. So polar grids have many useful practical applications, and today we're just going to scratch the surface and see how equations can be graphed on these polar coordinates. So let's review what we know from before. First, how to convert from polar to rectangular coordinates. So our first objective here is going to be not necessarily to graph on the polar coordinates, but we're going to cheat. How are we going to cheat? Well, we know how to convert from polar to rectangular. We are already familiar with rectangular. That's what we're comfortable with, you know, so we're going to graph things on our familiar XY coordinate system by converting from the polar equations we get into XY. So we're going to take all the R's and the thetas, and we're going to convert them into XY's, and then we're going to graph it on this. So that's our first objective. In the next objective, we're not going to cheat. We're not going to convert. We're just going to plot points and graph polar coordinates the way they're supposed to be graphed. But let's just use this one method first. Okay, and in order for us to convert all the R's and all the thetas into X's and Y's, we're going to use what we've learned in the last section. We know that X is equal to R cosine theta. We know that Y is equal to R sine of theta. We also know that tangent theta is X over Y. And finally, we know that R squared is equal to X squared plus Y squared per the Pythagorean theorem. So we're going to use all of these to convert from polar to rectangular, and then we're going to graph. Let's see some examples. Here is the first example. It says convert the following polar equations to rectangular equations, then graph on the polar grid. So here is the polar grid. Now, what they're asking us is not to graph this as a polar equation, but convert it into something that has X and Y instead, and then graph it here as if this was our X-axis and this was our Y-axis. So again, it's a way for us to cheat. But for now, I want you to go ahead and pause the video. Look at this. We have R sine of theta is equal to 3. How do you convert this part that has R and theta into X and Y instead? If you've forgotten, go back, look at the previous slide, and then convert this. What would this equation be in rectangular coordinates? Once you convert this, now you should be able to know how to graph it just in the regular XY coordinate. So go ahead and do that. Pause the video, do this, and then play it when you have figured it out, or at least tried. Okay, so from our conversion that we know that Y is equal to R sine of theta. So we can replace this polar expression with a rectangular expression. Instead of R sine of theta, we just have Y is equal to 3. And what kind of graph is this? This is the equation of a horizontal line that goes through the point 3 on the y-axis. So if right here, this is 1, 2, 3, 4, 5. The line y equals 3 is a horizontal line that goes like this. So we cheated a bit, but now we have graphed the equation r sine of theta is equal to 3 on the polar coordinate system by converting it into rectangular coordinates first. All right, let's see another example. What about this one, you guys? So go ahead and pause the video, do the same thing that we did before, and graph this equation on the polar grid. Okay, hopefully you were able to recognize once again that we can replace our cosine theta, this time with what? X. So x equals r cosine theta. That means this is the equation on the rectangular system of x equals -2. And if this is our x-axis and this is the y-axis, x equals -2 is a vertical line that goes through -2 on the x. So if on the x-axis, if we imagine this to be -1, -2, -3, -4, and so on, then x equals -2 is this vertical line that goes like this, parallel to the y-axis. And now we have graphed the polar equation, r cosine of theta is equal to -2. Here's another one, you guys. Theta is equal to pi over 4. Now this one is a little tricky because there's no conversion for just theta. Okay, we know that our cosine theta is x. We know that our sine theta is y, but we don't have any r's over here. We know that tangent of theta is equal to y over x. We also know that r squared equals x squared plus y squared. Okay, these are all the conversion equations that we have. So pause the video, think about which one of those would actually be appropriate for us to use here and how we can use it. You may not be able to figure it out. If you figure it out, that's great, but please try. And if not, play the video again and we'll go over it together. Okay, so the hint here is that there's no r, right? There's no r, we just have thetas. So we don't want something to have r cosine theta in it, so we don't want to use this. We don't want to use this one either. This last one is all about r squared, so definitely not. Here's the only option we got. Tangent of theta is equal to y over x. Well, how do we apply this here? There's no tangent, we just have a theta equals pi over 4. Well, we can take tangent of both sides of the equation. Tangent of both of these angles are equal. If both of these angles are equal, if the angle theta equals the angle pi over 4, then that also means that tangent of the angle theta is equal to tangent of the angle pi over 4. And that's the trick that we can use here. Once we have the tangents, now we can convert. We can use that tangent theta is equal to y over x. So now we can convert this from polar, from theta and r, into x and y. So y over x equals tangent of pi over 4. Now, what is tangent of the angle pi over 4? That's a known angle, isn't it? Definitely. This is the angle that we know. Pi over 4, 45 degrees, right? Here's the triangle, 1, 1, square root 2. So what is tangent of pi over 4? 1. that means this equation here, converted, is y over x is equal to 1. So now our conversion is complete. How do I graph this? Well, if you haven't gotten that far, I would recommend that you pause one more time, and if you had something like this in rectangular coordinates and you're asked to graph that, maybe you can take one more step. But how can we graph this? So pause it and then play it again after you've thought about it for a little bit. Okay, well, what you can do, because we know that we can graph any line in the format y equals mx plus b, right? That's the equation of a line. I can multiply both sides of the equation times x, because I don't want this x here in the denominator, or I can cross multiply, so to speak. Regardless of the method, you will reach y equals x. That's the equation of a line, you guys, right? This is the y equals mx plus b. What kind of line is y equals x? Well, first of, what is the y-intercept? 0. That's a line that goes through the origin. Our first point is right here. What is the slope? Slope is 1, or 1 over 1, so you go up 1 over 1 and so on. This equation here is the equation of the 45-degree line like this, which was one of the lines in the library of functions that we knew how to graph from before. That's the line y equals x with the angle 45 degrees, or pi over 4. We've graphed that line before. But excuse me, let me erase that. So this is just a way for us, again, to cheat, but now we're actually graphing the equation theta is equal to pi over 4. Now notice that this is easy in polar coordinates because this here is exactly that. That's the angle, pi over 4, right? So let's say I want to graph theta equals 3 pi over 4. Well, here's the angle 3 pi over 4 right there. So the equation of the line theta equals 3 pi over 4 is this line. Right? That's the equation of the line theta equals 3 pi over 4. What about this line in polar coordinates? What's the equation of this line here? Well, that's the line theta equals pi over 2. Very easy. So the equation theta equals an angle is just the line where that angle is. So that's one of the advantages of just graphing things in polar coordinates. This equation is very easy, and any equation in that format is very easy to graph in polar coordinates. Okay, let's summarize what we have here. So the equation r sine of theta equals a. Once again, r sine theta, when we converted it, it was y equals a, so that's a horizontal line. So r sine of theta equals a is a horizontal line. It lies a units above the pole, and it lies a units below the pole if it's negative. Same thing with our cosine. Our cosine, we converted this to x. So that was x equals a, which is a vertical line. So our cosine of theta equals any number is a vertical line that lies a units to the right or to the left of the pole. And finally, theta equals any angle is just a line that goes through that angle in polar grid. Okay, let's have some examples of other equations that we can graph, other polar equations that we can graph. We're still in the first objective, we're still converting. So now let's think about this. How do I convert that one into rectangular coordinates? Once again, let's write the conversion ones that we have. We got our sine of theta equals y. We have our cosine of theta equals x. We have tangent of theta equals y over x. We have r squared equals x squared plus y squared. These are the conversions that we have. So pause the video, think about which one of those can we use here and how. If this doesn't fit exactly, because now we need to get rid of this r, we need this r to become x and y. So which one of those can we use and what can we do to make it look like one of these? So pause the video, play it again when you're ready. Okay, hopefully you guys were able to recognize that we don't have any thetas here. So we don't want to use anything that has a sine of theta, cosine of theta, tangent of theta. This is the only one that we really would like to use. What's the problem? Well, the problem is our equation has just r. For us to convert into x's and y's, we need a r squared. So what can we do to get r squared? Well, there's two things you can think about. You can say, well, if I want to get r squared, I can multiply both sides of the equation times r. Well, not a bad way to think about it. It will give us r squared here, but then it will be r squared equals 4r. That's not very helpful. Sure, this one can be converted, but what about this r? Now you're stuck with r again, just like we had here. So no, that's not the way we want to go. If you didn't think about that, good. If you thought about it, now you know why we shouldn't use that. Okay, so what else can we do? We want to get this to be r squared. Well, we can actually square both sides of any equation. That's something that we can and we are allowed to do. So we can square the left-hand side, which will give us r squared equals, we can square the right-hand side, and that will give us 16. So that equation is the same thing as r squared equals 16. Now we can convert. We can replace r squared on the left-hand side with x squared plus y squared. Okay, now what kind of equation is this? If you didn't get this far, pause it again. Think about what kind of equation is that? How did we use to graph something that looks like this in rectangular coordinates? Then play the video again when you're ready. Okay, hopefully you've recognized that this is the equation of a circle in rectangular coordinates. What's the general equation of a circle? Well, the general equation was x minus h squared plus y minus k squared is equal to r squared. So what kind of circle is this? Well, in this circle, h and k are zeros, x minus 0, y minus 0. So the center of that circle, which is h and k, is what? 0, 0, the origin. That's right. This is a circle that has a center at the origin. All right, what else do we know? We know that this here is r squared, the radius squared, which means the radius of that circle is what? The radius is 4. Very nice. So how do I graph this circle? Well, I have the center. All I need to go is 4 in every direction. 4, 4. Right here again. And in every direction around that radius, I'm going to go 4 units, and then I connect them. That's the graph of that equation. It's a circle. So this is the graph of x squared plus y squared equals 16, which is a way for us to cheat. Again, we converted. So this is the graph of the polar equation r is equal to 4. Beautiful. Look at that. The polar equation r equals 4 is a circle that has radius 4. Very, very easy. So in polar coordinates, graphing circles is so easy. What is the equation of this circle right here in polar coordinates? The equation of that circle is r equals 2. The radius is 2. Very, very simple. Okay, just like when we graph the equation theta equals pi over 4 and theta equals pi over 2, very easy in polar coordinates. The equation of circles in polar coordinates are simply just r, the radius, equals whatever unit, whatever number the units of the radius is. Okay, awesome. Let's take a look at more examples. How about this one? Graph this equation, r equals 4 sine of theta. Okay, first we want to convert them into x's and y's. Let's write the equations again. We know that r sine theta is y, r cosine theta is x, tangent theta y over x, and finally r squared is x squared plus y squared. So pause the video. Think about this equation here. We have an r. We can't convert it right the way it is. We can convert r squared, right, like we did before. And here we have sine of theta. We also want to convert that. We want all the r's and thetas to become x and y's. So we have this equation here. This one does have sine of theta, but you can't convert just sine of theta. So what can we do? So think about it. I would recommend that you go ahead and see what you can do to both sides of this equation in order to convert it to x and y's, and then continue. What kind of equation is that going to be? What does that give us? Let's see. Pause the video, do as much as possible, and then play it again. Okay, well, in this case, what we did previously is not really going to help us, right? Did anybody try that? Did you try to square both sides? Not really going to be ideal. Sure, you're going to get r squared like we did last time, but then on the right-hand side, you get what? 16 sine squared theta? What are you going to do with that? Nothing here is going to help you convert a sine squared of theta. So no, there's no one size fits all, okay? Squaring both sides of the equation is not really the helpful operation to do here, but that's not our only option, thankfully. For both sides of an equation, we are allowed to multiply by anything that we want, as long as we do it to the left-hand and right-hand side. What can we multiply by here? That's right, r. How does that help? Let's see, the left-hand side now becomes r squared equals the right-hand side. You multiply this times r, we can write it as 4r sine of theta. This should look very familiar. R squared can be replaced by this, x squared plus y squared. This r sine of theta, all of that can be replaced with what? Well, all of that equals y. Okay, let's convert it. X squared plus y squared is equal to 4y. Nice. Okay, but now we're asked to graph this into rectangular coordinates. This looks a little bit familiar, but still very inconvenient. X squared plus y squared, that looks like the equation of a circle. If you thought about that, you would be correct. But then we have a 4y here on the other side. This is the tricky one. This is the one where we had to bring the y terms together, the y squared and the 4y, they had to come together, and we had to complete the square, which is what I was mentioning at the beginning of this lecture. How do we do that? Our first step is subtract 4y from both sides. Okay, what does that give us? It gives us an x squared plus. Now you want the y squared term minus 4y, you want those to be together. You're going to complete the square here, okay? You're going to have to add something over here. Equals, what do we have left on the right-hand side? 0. Why do we want to complete the square? Because the equation of a circle, guys, has to be something that looks like this. You know, x squared or x minus h squared plus y minus k squared equals to something. That's the standard form of the equation. X minus h squared, in this case h is going to be 0 plus y minus k squared. We still don't know what this k is, equals r squared. This is our goal, to make the equation look like this, because that's the equation of a circle. So that is why we need to complete the square here, so we can get a perfect square down here. All right, what trick do we know for completing the square? I've mentioned it earlier. Okay, how do we know what number we need there to complete the square? Well, here's what we said. You take the middle term, in this case is 4, half of it, okay, so you divide that by 2, 4 divided by 2, and then square whatever you get, okay? So take the middle term, divided by 2, and then square it. What do we get? 4 divided by 2 is 2, 2 squared is 4. So that tells us that to complete that square, we need to add 4 here, plus 4, okay? Very nice, very convenient, but we can't just add 4 to one side of the equation, right? This is the left-hand side. I also have to add 4 over here to the right-hand side. So that is how we complete the square. You add whatever number you need to both sides of the equation. Okay, and what complete square does that give me? Y squared minus 4y plus 4. That's a perfect square trinomial. So if I factor that, I get y minus 2 squared is equal to, the right-hand side now is 4. Okay, and we've reached our goal. We do have the equation of a circle here. It's in the standard form. What is the center of this circle? H and K. It's going to be what here? So H in this case is 0. K is what? 2. So the center is 0 and 2. What about the radius? So this is r squared right here. That means the radius is 2. Now I have everything I need to graph that circle. Center is 0, 2. So if this is the x and y axis, the center 0, 2 is right here. Okay, 0 on the x, 2 on the y, and the radius is 2. So from the center I go 2 in each direction, 2 units, equal units, right there. Okay, what does that circle look like? There we go. And that is the graph of the polar equation r equals 4 sine of theta. We graphed it once again by cheating. We converted from this to rectangular coordinates because we know how to graph circles in rectangular coordinates. We first had to complete the square, which we also know how to do. We've done that in previous courses. That gave us the center and the radius, and we graphed it in that way. Let's notice a few things here. Notice the symmetry. This graph or that circle is symmetrical about the line theta equals pi over 2. Remember, the line theta equals pi over 2 is this line right here. Okay. So in other words, the y-axis, right? This graph, this circle is symmetrical about the y-axis if we're talking about rectangular coordinates. This is going to come in handy later, right? So 4 sine of theta is symmetrical about the y-axis. And just so you know, the general equation of a circle in the polar coordinates in that format, let me erase this for now. You can go back if you needed to copy something. But if I have an equation in a format r equals 2a sine of theta, in polar coordinates, this is an equation of a circle, as we can see. The radius of that circle is a. So if this number here is 2a, that means the radius, you take this number and you divide it by 2. Okay, so here a equals 2, which is the radius, which is exactly what we have right there. Okay, and the center is 0, a. So the center is 0, 2 in rectangular coordinates, which is what we've seen here. So if I put this in rectangular coordinates, this is the point 0, 2. So this equation, this polar equation, is an equation of a circle with those specifications, which we have seen again using an indirect way of first converting to rectangular. All right, let's see one more example. This time I'm going to encourage you to do this one on your own. You have all the tools that you need, okay? If you have understood the previous example very well, you should be able to do this one also on your own. If you get stuck, rewind, follow the last example. It's not going to be exactly the same, but it will be very, very similar. First step, go ahead and convert this into rectangular coordinates. Now, use the rectangular coordinates to graph. All right, if you need to you need to complete the square. Go ahead and complete the square. Kind of try to follow the steps of the last example with a little bit of a difference there, but it's the same exact concept and idea. So go ahead and do that, you guys, and then play the video again when you're ready. Okay, let's try it. So first, we've seen the trick here. What do? We can multiply both sides times r. That gives us r squared is equal to -2 times r cosine of theta. Now let's convert. Just like last time, we know that r squared, we can replace that with x squared plus y squared. And now r cosine of theta, that can be replaced with x. X squared plus y squared equals -2x. Now once again, this is also the equation of a circle, but now we do have a term that has an x in it on the right hand side. So this time we're going to add it here, but this term, because it's an x, it needs to be bundled with the x squared term on that side. So this is going to be x squared plus 2x. Now that's the one this time that needs to complete the square. Okay, this is the one here that's going to be x plus something squared. All right, so we can leave some space here for whatever number we need. Then we have plus y squared. Okay, this one we're going to leave alone, is equal to 0. Okay. So let's think about what we need to complete the square here. What number do we need? Same concept, take the middle term, which is 2. Take half of it, means divide it by 2. So 2 divided by 2 is 1, and then square that. 1 squared is 1. Which means we have to add 1 here to the left-hand side. Therefore, we also need to add 1 here to the right-hand side. Okay, now let's complete the square. So let's factor this perfect square trinomial. What does that give us? That gives us x plus, this time it's plus, not minus, because the middle term is plus. This is x plus 1 squared plus y squared is equal to 0 plus 1 on the right hand side is 1. And there we have it. That's the equation of our circle. Once again, the general equation is x minus h, be careful with this minus h by the way, plus y minus k squared equals r squared. If you did not get this, pause the video again now. Based on this equation, guys, what is the center? Find the center of that circle. What is the radius? Find the radius of that circle. Go ahead and graph the circle. Okay, so if you haven't done so already, pause the video now and at least extract this bit of information and graph it and play again when you're ready. Okay, so the center is h and k, but this is x minus h. This is x plus 1, so h in this case is what? It's not going to be 1, it is a -1. H is -1, because this can be as if you can treat it as x minus -1, so that's the x minus h here. Okay, h is -1, k is what? Well, that's y squared by itself, so it's y minus 0 squared. So k is 0, that's our center. negative 1, 0. What is the radius? Well, this here is the radius squared. Take the square root of that. Square root of 1 is still 1. So this is a circle with the center as negative 1, 0, if we're talking about rectangular coordinates. So that is this point right here, negative 1 and 0. And the radius is 1 unit. So it's 1 unit in every direction around that radius, around the center, excuse me. So we can connect all of these and graph the circle this way. And that is the equation r equals negative 2 cosine of theta. Okay, a couple of observations, you guys. Notice that the symmetry in this case is different. Okay, it's not symmetrical about the y-axis anymore. It's symmetrical about this right here. This. Okay, this is the polar axis. In polar coordinates, that's the polar axis, remember? So polar axis or the x-axis. Okay, and let me erase some of this. Okay, and the general equation of these circles in polar coordinates r equals negative 2a cosine of theta. So in this case, a is the radius. So right here we have negative 2. The radius is negative 2 times a, so that means a in this case equals 1, which we've seen is true. The radius is 1. And also this has a center at negative a, comma 0, which we've also seen here. The center is negative 1, comma 0. So in general, an equation in this format, once again, is a circle with the radius a and the center negative a, because this is negative a, comma 0. Okay, so this is the last example that we're going to do with converting to rectangular equations first. The next examples we're going to see are going to be examples where we're not going to convert. We're actually going to use the polar coordinates and polar expressions we've learned. But let's summarize those ones that we've seen first. So first we've seen r equals 4, or r equals any number. This is a circle with, so if this is r equals a, where a is any number, circle with radius 4. And the center was 0, 0. The next example we've seen is this, r equals 4 sine of theta. This is, we've seen that this is a circle in that format. Radius is a and the center is 0, comma a. We also noticed that there's a symmetry. When we had a sine, the symmetry was about this line, or the y-axis. The next one, we had a cosine, and the symmetry was about the polar axis, or the x-axis. So keep those two symmetries in mind. They're going to come in handy later. But this, again, is a circle this is also a circle. That's this case right here. It's a circle with the radius a, and the center is negative a comma 0. And those two are here are exactly the same thing, one of them with the sine and one of them with the cosine, but this time there's a positive and the negative, the positive and the negative. So we've seen an example of both, one positive and one negative with each. So that is the summary for those, and for converting first, in order to graph this, we can convert into x and y, and then we can graph it. This right here is just some information about the symmetry that we've seen. And this is the first one we talked about. When we have a sine, it is symmetrical about the y-axis, or this line right here. So any point, here's the y-axis. Any point in polar coordinates that's going to be on that side is going to have its symmetrical point on the other side about the y-axis. And anything that has a cosine of theta is going to be symmetrical about this line right here, the x-axis or the polar axis. So any point above the x-axis is going to have its symmetry below. So you should write this concept down. So once again, equations with cosine of theta, they're going to be symmetrical about polar parentheses x-axis, and then equations with sine of theta, they're going to be symmetrical about the line theta equals pi over 2, which is the y-axis. Okay, so cosine, x-axis, sine, y-axis. So write this concept down. We're going to use it. This here is a brief explanation for why that is. You should check it out if you want to. This one here is because of the even-odd identity, or the even-odd property of cosine. We know that cosine of negative theta is the same as cosine of theta. So this is interesting. You can read it if you want to, but this right here is what I expect you to know. So that's the important part here. When you have cosine, what kind of symmetry is that going to be? When you have sine, what kind of symmetry is that going to be? So we're going to stop right here for our first objective, and we're going to get into the next objective in the following video.